Right. Quantum supercomputers. Why is it important to talk about this topic? Well, besides being just the coolest combination of words and the inspiration to this amazing face mesh between these two gentlemen, anyone can tell who are these two people? Turing and Bohr, right. I find that it's hard when you put two half faces. But yeah, even putting, and by the way, this is, you can see that I'm very proud of this because it's human-generated face mesh and not AI-generated, fully human-generated. But besides all of these critical facts, I think that this concept of a quantum supercomputer is actually very important, it's fundamental to the progress in our field. So we are all here today because we believe that quantum computers could perform some computational tasks much faster or much more efficiently than our regular classical computers. And I believe that this concept of a quantum supercomputer is really all about demonstrating just that by squeezing the most we can, the most of the performance we can out of both the quantum and classical compute resources and their integrated system. That's perhaps the easiest way to get to a real quantum advantage demonstration. Some people claim the only way, in fact. More concretely, the importance of quantum classical integration has been increasingly and actually critically discussed over the last several years, where we could see that at every step along the way towards useful applications, from calibrations, error mitigation, error suppression, error correction, of course, hybrid applications, etc., we really need classical compute close by to the quantum compute. And every year, every month, actually, there's new research, new ideas, new demonstrations that show that the more classical compute power we bring closer and closer to the qubits with lower and lower latencies between the two, the more we can push the performance of these integrated systems. And these different steps along the way can be optimized further. So today, I want to tell you how our unique approach to quantum control at quantum machines, which we call hybrid control, really unlocks this concept of a quantum supercomputer. At quantum machines, quantum classical integration is actually at the very core of the company and one of the core reasons why we founded quantum machines. From the postdoc work of my co-founder Nissim Ofek in his postdoc at Yale with Professor Rob Shulkov, where he demonstrated quantum error correction for the first time with superconducting qubits, and all the way until today, quantum classical integration, integrating classical compute into our control systems and bring them as close as possible to the qubits, is the one thing we think about the most at quantum machines. So today, I'm actually very excited to tell you about our journey to this concept of a quantum supercomputer. So our journey really starts in 2019 when we launched our first hybrid controller, the OPX. The OPX was the first controller that brought completely general classical compute engines into the heart of the control system, which means that actually from the same chip that produces the quantum operations and sends them to the qubits, in the same chip could perform classical compute operations. And this also meant that for the first time, you could from a single programming language, our programming language, hybrid quantum classical programming language, you could write classical compute operations in the lowest level, what we call the pulse level control programs. So you can see this example here. We measure a qubit, and then the result goes into these classical variables, and we can process those variables completely classically, and then based on the result of this classical processing, we can respond with other quantum operations. And all of this is done in real time with very, very low, what we call feedback latencies or feed-forward latencies. So the time it takes us to measure the qubits, process them on the classical side, and respond is actually the fastest in the market with our technology. And you see, this combination of being able to do it very smoothly with really nice user interface, together with this real-time hardware performance, was, I believe, the reason why our technology was pretty widely adopted by the community with hundreds of customers around the world. So then after we launched OPX, we started interacting a lot with customers around these hybrid use cases, hybrid quantum classical use cases. And so at some point, we wanted to understand better how we can define rigorously this concept of quantum classical processing or quantum classical integration. We do a lot of research on the topic. This is a paper we released in 2023 where we categorize the different quantum classical hybrid use cases according to both what type of adaptation do we need to do to the quantum operations based on the classical operations that were done before. That's the x-axis that you see there. And then the y-axis categorizes the different use cases based on the feedback or feed-forward, we call it feed-forward latency requirements. How fast do we need to close the quantum classical loop? And what was very cool is that with a single machine, with the OPX, we could unlock all of these different categories of use cases. And I want to just give you a few examples for that. So mainly focus on the y-axis here. We call it QRT, or quantum real-time. That's when we respond, we do the quantum classical loop faster than the coherence times of the qubits. Then we have SRT, system real-time. That's where we close the quantum classical loop faster than some of the classical parameters drift times. Parameters drift over time in the system, and we need to correct for those. So we need to be faster than that. And finally, we have this quantum near real-time, NRT, where we just compare things to the total runtime of the application in order to see where the bottlenecks are. So the first example I want to give you is in our work with Google. So this is very cool collaboration where we enabled feed-forward operations, mid-circuit measurements and feed-forward operations on the Sycamore chip at Google. So you could actually do these adaptive circuits, as we call them, measure in the middle of the circuit, process the qubit states classically, and respond with conditional operations with a latency which is significantly lower than the coherence times of the qubits. In this particular case, we created large-scale GHZ states and large-scale entangled states with the lowest feed-forward latency that, for our at least as long as we know, have been reported in producing such feed-forward based states. So this is quantum real-time. This is another cool example, which is more around system real-time from Professor Andrew Zurak, CEO of Dirac, and also professor at UNSW. So Dirac, to initialize their qubits, they need to actually do a very complicated sequence of feed-forward based control. Not going to go into the details, but you can see this diagram here on the left. Very complicated real-time decision-making based on qubit measurements, and again, they could do it because of the OPX. On the right side, you see also that while they're doing these protocols, they keep correcting for the drift of certain parameters of the system. This is why I meant in system real-time. And so you see the upper figure is more kind of dirty or kind of wiggly than the lower figure, because in the lower figure, they're actually correcting in real time using our real-time quantum classical operation and very low feedback latency. So this is critical. I think that the OPX is the only controller in the market that actually allows doing such complicated quantum classical hybrid protocols. Lastly, an example from Alice and Bob. So here, Alice and Bob is performing these beautiful Wigner tomographies of their CAD states, CAD qubits. And this is an example of near real time because it takes a lot of time to characterize the CAD qubits using these Wigner tomography, beautiful two-dimensional figures that you see here. They take hours. But without the quantum classical capabilities of the OPX, they would take way more than that. And you wouldn't even be able to take them with such high resolution. So I think that's a nice example that shows that also just to speed up things, quantum classical integration is very important. And we sometimes miss that. Okay, so that's very cool. OPX enabled all of these quantum classical hybrid use cases, but this is not enough. And the reason is that our first generation that we launched in 2019 was really working very nicely, but for small scale, maybe up to 50 qubits or so. So we need to scale this up. So in 2023, we launched our flagship product, the OPX 1000, which really brings this hybrid approach to quantum control, brings it to a whole different level of scale. So the OPX 1000 actually has the highest control channels density in the market, while it also brings down the price per qubit down. And at the same time, it actually pushes to new limits the analog performance, the analog specifications, which are very critical as we make higher and higher fidelity operations and better qubits. So when you make better and better qubits, the control system can limit the fidelity of the operations if the signals are not pure and clean enough. So at the same time, we scale up, we lower the price per qubit control, but we improve the specification. It seems pretty contradictory, but it actually has very good reason. This is enabled by the fact that we're starting to integrate lots of functions that used to be done with discrete components into a single silicon chip. So in this case, this is an example for a direct digital synthesis technology, which takes up conversion of signals to high frequency and brings them into the silicon chip that can produce now the entire microwave signal in silicon. So moving to DDS technology was a key enabler to really scale up the system. It both improves the specification while it simplifies the system dramatically, as you can see, because we have much, much less components. So power goes down, cost goes down, etc. It also enables all kinds of features that I won't go into, but very cool technology that we're using these days. And we plan to do more and more of that, bring things into silicon. So this is how we scaled up the control system to about a range of up to 1,000 or a few thousands of qubits. But even that is not enough, right? Because we also need to scale up the classical compute that we integrate with the quantum control. And we took the very big first step in this direction when we decided to, about 2 or 3 years ago, to develop together with NVIDIA DGX Quantum. This is really the first tight integration between QPUs, or the quantum control system, and high-performance compute resources. So for the first time, this system allows communication latency between the quantum control system and the CPU, GPU superchip of NVIDIA, the Grace Hopper, with less than 4 microsecond round-trip latency. We're actually bringing this down even further these days. So that's very cool. And this system can be programmed all from software, from Qua, our language, CUDA, and CUDA-Q. So it brings all of this real-time hardware performance again with all of these nice user interfaces, software programmability, and libraries. Okay, I just wanted to mention that DGX Quantum is not just about. So we think a lot about quantum error correction in this context. We believe that this architecture is really optimized for quantum error correction, but DGX Quantum is not only for quantum error correction, it also is built a lot in order to accelerate calibrations. This is a cool example where we optimize a GHZ preparation protocol using reinforcement learning. I won't go into the details, but you can see how these steps of reinforcement learning, optimization, and running a quantum circuit and measuring the fidelity of the state preparation are interleaved, and how the parameters then converge over time. We have a learning phase and then convergence phase, and this is very cool experiments that were already done with the OPX and the Grace Hopper chip, so the DGX Quantum system. Okay, so DGX Quantum is now in its alpha program. It's an early adopters program. We already have several customers that are using it, and we have a long list of people waiting for the beta program to be opened very soon. So we hope that we can show many cool examples of quantum classical hybrid programs or applications running on the system very soon. All right, so what's next now? So we still need to scale up the system. So we're at maybe 1,000 or a few thousand qubits range, but we're aiming for much more, right? So everything I showed you so far is what we already did. What are we doing next is, again, we need to scale up the control system and scale up the classical compute. So first, for scaling up the control system, QM is very well positioned these days to really go do what's really needed in quantum control to do massive scaling of the control system. The control system is starting, at least in some qubit platforms, to become really the bottleneck in terms of cost, power, size, and therefore we have to continue this approach that I showed you before, that to go ASIC, to go with much more advanced ASIC technology in order to bring down cost, power, and size. And we actually built, from the beginning of the company, a very dedicated team that is coming from the right places in the industry to build such ASIC components. We raised quite a lot of money so far, $260 million overall, from investors that also bring a lot of knowledge in the ASIC industry, and we are planning to do ASIC development to scale up control systems. We're not doing it alone. It's very important for us to partner with our customers. This is an example where we recently established this consortium with HPE, Synopsys, Colab, Applied Materials, and others in order to build the architecture and the technology stack that is needed for scaling, to hundreds of thousands of qubits and more. And so this is not just about scaling up the quantum computer. It's also about integrating it with supercomputers, and this is the full vision of a quantum supercomputer. So we have the architecture that we also put in our position paper about a year ago with, again, the same group of companies that I mentioned. I'll show this architecture maybe slightly more simplified here. So you see we have those 3 layers of and that are connected also with 3 different networks. We have the network of the controllers, of the OPXs, that are connected with a very, very low latency networks, hundreds of nanoseconds of communication. Then we have the blue network that connects now what we call the dedicated quantum acceleration servers to the OPX or to the controllers network. So here you can see we connect different servers that can host different accelerators such as CPU, GPU, but also FPGAs, ASICs, with microsecond latency over a similar network to what we showed in DGX Quantum. So we're scaling up this now. And then, of course, the pink network, which is the typical network of the supercomputer, the HPC network. So I think I'm almost out of time, so I wanted to show kind of like how a workflow of a hybrid application would work on this architecture. So you would compile a quantum error correction circuit on the pink node, and then it would go to the blue node to initiate what we call the logical circuit orchestrator. That will then in turn create a decoder stack on the blue nodes, but also the controller programs. The controllers would start working, taking data from the qubits and measuring syndromes, sending those syndromes back to the blue network for decoding, et cetera, et cetera. I won't go into all of the details here because I think I'm really running out of time. The important thing is that we are working on this. We already have the basic components with the OPX 1000 and the DGX Quantum. We're scaling based on this architecture, on this proof of concept technologies, to much bigger numbers. And with that, I think I will summarize that this is our journey to quantum supercomputer. We started really from the bottom of the stack with the OPX, connecting quantum and classical really in the controller. Then with DGX Quantum and our OPNIC, which is the interface that we make to the acceleration servers. And the next step is really to build a full-fledged quantum supercomputer. So with that, let me thank you.